Welcome back. Let's cover our last chapter in this unit, which, as promised, is a short one. This chapter is on ethers. And I think you recall ethers from when we discussed functional groups. You're aware that they are essentially another organic derivative of water. They can be thought of that way, just as alcohols can be thought of that way. Generally, you name them by identifying the two groups, the two alkyl groups or hydrocarbon groups that are attached to oxygen, and those two R groups can be either the same or different. So for instance, this compound up here, where the groups on the oxygen are a butyl group and an isopropyl group. Well, butyl comes before isopropyl in the alphabet, so we call that butyl isopropyl ether. If the two groups are the same, like in this case, you could just call that compound diphenyl ether. Some people actually would just call that compound phenyl ether. Just like you might have heard of something colloquially just called ether. That is actually diethyl ether, and some people call that ethyl ether. Diethyl ether has been used in the fairly distant past as an anesthetic. If you inhale enough of it, you will go unconscious. Actually, it's rather a nice odor, although I've never inhaled it to that degree, but you'll probably use it in organic lab at some point. It's a very commonly used solvent, and it's not particularly dangerous, apart from being stupidly flammable. And of course, I wouldn't go drinking it or taking a bath in it, but if you get a little whiff here and there, it's not going to hurt you. But I'm not a fan of calling diethyl ether ethyl ether or diphenyl ether phenyl ether, but you will sometimes see that done. Sulfides, which aren't really mentioned much here in the book, but I can't help mentioning them. They're simply the sulfur analog of ethers. So you name them just the same way you would name ethers. And just like thiols, sulfides also smell real bad. I mention here in the class notes, because ethers have no OH bonds, they do not exhibit hydrogen bonding. I probably should have said something like they're not able to donate hydrogen bonds. They can accept hydrogen bonds. So if a water molecule got close enough to an ether molecule, you will form a hydrogen bond where the oxygen in the ether acts as a hydrogen bond acceptor. So something like that could happen in limited cases, but they don't have full-on hydrogen bonding like water and alcohols and primary and secondary amines do. So that's why they have much lower boiling points than alcohols, other things being equal. And that comes to why diethyl ether, which actually is this compound here, why that is such a commonly used solvent. Its boiling point is under 40 degrees Celsius. So it's real easy to get rid of when you're done with your reaction. Very, very easy to evaporate off. Just don't light a match, and you'll be fine. So, here again, I'm just going over why ethers make such good solvents. And I think it begins to make sense when you put a little bit of thought into what do we want out of a solvent when we run a chemical reaction. How do we know what solvent to choose? Well, there are some properties that we want solvents always to have. One is we want it to dissolve everything, right? Or mostly dissolve everything. And ethers are right there at that level of polarity that they're pretty polar, can dissolve a large number of different functional groups, fairly polar functional groups, but not so ridiculously polar like water that it's too much. We also want, out of our solvents, it would be preferable if it were a liquid at room temperature, or at least at the temperature that we want to do our reaction at. And of course, if you want to do a reaction at higher than about 35 or 37 degrees Celsius, well, diethyl ether is not a good choice. That boils too low. But that's not very often the case. And so if you wanted to run a reaction at room temperature, or even at 0 degrees Celsius, even at below 0 degrees Celsius, there's ways of doing that. And diethyl ether is an excellent choice for those conditions. And the other thing we want from our solvent is we want it, as we mentioned the last time, we want it not to react with anything. And that's why ethers make such excellent solvents. Ethers are very inert. They don't do very much chemically. There's maybe one reaction that ethers undergo, and I'm skipping that section in your book because they do it a very different way than I've ever done before, and I think it's needlessly complicated. But suffice it to say, to get an ether to react, you really have to kick it. You have to kick it hard. You have to use really reactive compounds. So, but diethyl ether is a very commonly used solvent. Another ether solvent that's quite common is the five-membered cyclic ether. Looks like this. I'm having you not be responsible for the section on cyclic ethers, but I don't think most of the details in that section are important to you. I really don't care if you memorize particular ones or their names. But I think you're already aware that ethers can be cyclic. And this particular one, which I'll just let you know, it happens to be called tetrahydrofuran. I really don't care if you memorize that name. But that's another very commonly used solvent. Sometimes we lovingly call it THF for short. It's a little different from diethyl ether. It's quite a bit higher boiling. And an interesting feature of THF is that it's water soluble to quite a large extent, which means it's actually kind of a pain in the backside to get rid of. You know, if you use diethyl ether as your solvent, diethyl ether is not water soluble really to any degree at all. And so I don't know if you've done any extractions yet in lab where you partition your reaction between an organic solvent, which almost always floats on the top, unless it's a dense organic solvent like dichloromethane, and then you have your aqueous layer on the bottom. And then you can separate your two layers and clean your organic layer out of a lot of inorganic crap. You don't have that luxury. What am I doing with my compounds today? Goodness, they're going to sue me for turning them into all these horrible shapes. But anyway, you don't have that luxury with THF because it's water soluble. So you have to go to other methods. But both of the ether solvents of all kinds exist. There's methyl tert-butyl ether, which we're going to talk about shortly. Dimethoxyethane gets some use. So there's others as well. But I would say by far the most commonly used one is diethyl ether. How do you make ethers? Well, the old way of making ethers was very limited. Essentially, you would condense two molecules of an alcohol by treating the alcohol with an acid catalyst. And what would happen is two of the alcohol molecules would come together and make an ether molecule plus water. Water is the byproduct of the reaction. And that works, but it's very limited. You can only make symmetrical ethers, for one. And also, you can only use primary alcohols. Otherwise, the reaction doesn't work, because it goes by an SN2 mechanism, very similar to what we talked about in chapters 6 and 7. So making something like butyl isopropyl ether would be out of the question with this reaction. If you did want to make a reaction like that, the way you would do it is with a method known as the Williamson ether synthesis, which I'm describing over here. Here's an example of a Williamson ether synthesis. And by the way, in every conceivable way, this is not a new reaction. You already know this reaction. It's just an SN2 reaction. The only thing we're going to do is make sure that our nucleophile is an alkoxide ion, the conjugate base of an alcohol. And so how do you deprotonate an alcohol? Alcohols are weak acids. They have a pKa generally in the high teens. There's a couple ways to do it. There are really strong bases that will pull that proton off for us. Another way to do the reaction is by treating the alcohol with an alkali metal. Sodium is used quite often. Again, I want to stress this is elemental sodium. This is sodium metal, not sodium cation. Yes, that's stuff that you throw it in the lake and there's a big fire. Trust me, I would not want to do that. I would be very scared. I've had alkali metal fires before, and one of the things that I struggle with greatly with my students is convincing them that fires are bad. Usually I'm not able to get over the hump and convince very many people. But you will be convinced that fires are bad if, God forbid, you ever have a fire that you did not intend to have. Then you'll learn real quick that fires are bad. Good. You can treat an alcohol with sodium metal or lithium or potassium metal. Any of these would work. I would probably use sodium because it's readily available, it's inexpensive, and it's fairly reactive. And this reaction, again, I couldn't draw curved arrows for a mechanism for you. This is a redox reaction in which the sodium metal gets oxidized to Na+, so the oxidation number goes up from 0 to +1, and the hydrogen in the alcohol gets reduced from having an oxidation number of +1 to an oxidation number of 0. You get elemental hydrogen out of this, and that bubbles out of the reaction vessel. Don't light a match. Very, very dangerous. But aside from these inorganic pieces, the organic portion that you get is the conjugate base of the alcohol, the corresponding alkoxide ion. And R can be anything. This reaction is very general. So it's very straightforward to make an alkoxide ion in this way. So for instance, we could make methyl tert-butyl ether this way. You could also make butyl isopropyl ether this way. I'll even let you know you will want to use isopropyl alcohol and 1-bromobutane. So see if you can figure out how to make butyl isopropyl ether with a Williamson ether synthesis. In fact, we call it a Williamson ether synthesis, but you can make sulfides very easily with this method. It's the exact same thing. You could make diethyl sulfide by treating, let me see, bromoethane with the conjugate base of ethane thiol, CH3CH2S-, which is even easier to get than an alkoxide ion. So those would be worth your while trying to figure out how those work and what those mechanisms are. But they're simply SN2 reactions. You can make an ether or a sulfide by a Williamson ether synthesis. And that ether or sulfide can be either symmetrical or asymmetrical. So I've given you some ideas there. If you want to stop the video now and look at it, you may, or and play what I said several times so you get all the details. Or if you want to think about it later, that's also fine. But methyl tert-butyl ether used to be a pretty important compound. Actually, the correct name would be tert-butyl methyl ether because the tert doesn't count, I believe. Double check me on that. And B comes before M, so the official name would be tert-butyl methyl ether. But it started getting called MTBE for methyl tert-butyl. I don't care, to be entirely honest. The difference is so slight. I think both names are perfectly clear and perfectly acceptable. But MTBE was used for quite a long time as a gasoline additive. It would increase the octane rating of the gasoline, but methyl tert-butyl ether is un poco toxic, and so they started using ethanol instead for the same usage, which also is the added benefit of giving a lot of business to the corn growing industry, which that's totally fine. But methyl tert-butyl ether is pretty easy to make from tert-butyl alcohol. You treat your tert-butyl alcohol with sodium or lithium metal, you'll get the alkoxide ion. And there then follows an SN2 reaction. You'll treat the tert-butoxide ion that you get from this with, wait a minute, I'm not quite sure that's selected. There we go. You treat this, once you've converted some of your alcohol to the tert-butoxide ion, you treat it with methyl iodide. Here's your alkyl halide. It's not just primary, it's methyl, so that'll react really well. And this will undergo an SN2 reaction like any other. The alkoxide ion will attack the methyl carbon. The iodide ion will leave. We break the carbon-iodine bond. And in the end, I suppose you'll get some sodium iodide in addition to your methyl tert-butyl ether. So it's quite easy to make these, to make ethers or sulfides by the Williamson method. And it's a reaction you know already. It's simply an SN2 reaction. So, like I said, officially we're skipping the section on cyclic ethers, but I would certainly like you to know that cyclic ethers exist. I don't care if you memorize any particular ones, but you know, we went over the structure of tetrahydrofuran before. Structures like that should not surprise you, that you can have such compounds. Good. So there is one other class of ethers that's special, and those are known as epoxides. Epoxides are cyclic ethers with a 3-membered ring, and they're pretty easy to make from alkenes. you treat the alkene with a peroxycarboxylic acid. So this is a typical peroxy acid over here. It's not the only one that you can use. That compound is called peroxyacetic acid, and I gave that name in the class notes. And memorizing the name is not what's important here, but I would like you to see that this compound is basically acetic acid, but with an extra oxygen in it. So this is it's a carboxylic acid that's also a peroxide at the same time. And so these are very good oxidizing agents. And you won't be responsible for the mechanism. It's known. I could show it to you, but you're not responsible for this mechanism. But essentially what happens is one of these oxygens, in fact, I should be able to specify which, it's actually that oxygen atom winds up getting inserted into the alkene, in between those two alkene carbons. And I give you a step-by-step method showing how to go from an alkene to the epoxide, so you can figure out what the structure of the epoxide is that you would get from an alkene. I'm just using cyclohexene as an example, but I could have picked any alkene. And this methyl group on the peroxyacetic acid, that can be anything. There are a wide variety of other peroxy acids that are also used. Peroxytrifluoroacetic acid is another one. So instead of CH3, you have CF3. There's another one called MCPBA. Since a lot of you are already going to think that is hilarious and dying to know what it looks like, I will show you. So we have a chlorine over here. And over here we have that same COOOH group, CO3H. So the same functional group that you see over here. This is your MCPBA for metachloroperoxybenzoic acid. And I only mention it, I hesitated to mention it, but I didn't see it when I looked through the OWL questions, but you know our luck. Some of you are going to run into that in OWL and be like, oh my goodness gracious, what is that? Well, MCPBA is just another peroxycarboxylic acid, like peracetic acid. Any of these can be used. You can even use just perbenzoic acid without the chlorine. That's also available. So any peroxycarboxylic acid will do the job. And that converts alkenes cleanly to epoxides. Like I said, you are not responsible for the mechanism. It's known, but it's somewhat complicated, and there's already enough on this exam. One thing to be aware of, and the reason that epoxides are special is because they're exceedingly strained. I think we've talked about small rings, and we've said how rings that are smaller than 5 or 6 membered are quite strained because the bond angles are very far away from the ideal sp3 hybridized bond angle of 109.5 degrees. And in fact, in any 3-membered ring, those bond angles are by definition 60 degrees. They may not be exactly 60 degrees in an epoxide. In the cyclopropane, they would be. Whatever they are, it's well short of 109.5 degrees. And so as a result, there is a section in the book, which you will not be responsible for, that shows how epoxides can be opened by treating them with any of a variety of nucleophiles. And by the way, these are nothing more than SN2 reactions. So these are usually done in basic medium. So in basic medium, we're okay with things with minus charges, but this can be an oxygen nucleophile or a nitrogen nucleophile or even a carbon nucleophile. And when that nucleophile attacks either one of those epoxide carbons, you break one of those carbon-oxygen bonds, and that releases a significant, a tremendous amount of energy in the form of strain by breaking open that 3-membered ring. So that's why epoxides are special. Like I said, I really wanted to avoid, especially given the circumstances of the rest of the semester, I really wanted to avoid all those cans of worms. So I'm satisfied if you're aware that epoxides exist, if you know how to make them from the corresponding alkene, and you're aware that they're special. They're very, very reactive because they're so strained. I think that's more than enough. I'm happy with that. And with that, we are done with the material in Chapter 8. And also with that, we're done with the material for exam number 3. So sometime soon, okay, I'm lying, maybe not soon. Hopefully by like next Tuesday, Wednesday, I'll start putting up material from chapter 9, which I believe is next. And actually, you'll be entitled to some chapter 9 material the week after next, the Thursday. So certainly by Thursday morning, I'll do my utmost best to get some chapter 9 material up on YouTube. Other than that, have a great day. We'll see you next time.